Okay, so I'll just say a few words. Thank you all so much for coming. I really appreciate your interest. I'm Professor Victoria Interrante from the University of Minnesota. I've been a faculty member there for about 20 years, working in the field of virtual reality, virtual and augmented reality for about the past 15 years. And I'm going to be talking to you today about just a tiny little bit of my of the research that I've been working on, focused on facilitating accurate spatial perception in immersive architectural environments. So how does this, interesting, okay, there we go. So I've been working over about the past 15 years, like I said, with architects to try to improve the potential of virtual reality technology to facilitate the process of conceptual design in architecture. And this is my colleague, Lee Anderson, and this is a picture of some work that we did way back in 2003. And Lee was inspired by the potential of virtual reality to allow people to experience their designs before they were built. He said that if you could give any architect, like if you asked any architect what's one thing that they wish they had, and that would be the ability to experience their designs from a first-person perspective, because it's very difficult to imagine the feeling of a space just from looking at a picture of it. You know, the feeling that we get in this of the soaring ceiling, it's something that's you know, a picture can't really convey. And so our work with this started way back, and it has many opportunities for virtual reality. So first, like I said, immersive, the first person's experience of a proposed space is difficult to imagine just from a non-immersive representation, either from a floor plan or even seeing it on a desktop monitor. What was most compelling to Lee, though, because he was a professor of architecture, he's now emeritus just a couple of years ago, but as a professor of architecture, he said that when you're teaching students to think about creating a space, there's so many things about the process of architectural design that encourage you to think of the building as an object to be admired from a distance. So you're big, the model is small, you're here, the model is there inside the computer, or it's there on the paper, or it's there, you know, as a little thing made up of cardboard. And so what that does is that encourages you to just start focusing on details of the design that are appealing to somebody from a bird's eye perspective. And he said that it's equally important for students to think about a building from the point of view of its occupants as a space to be enjoyed. And our building, the building that I have my office in right now, is the quintessential example of a building that won an award for its architect. It's got all of these features that look lovely from the building across the street, but as a place to have an office, is in a place to encourage collaboration and just, you know, sunlight and all sorts of things that you want as an inhabitant of the building, it's lacking because it wasn't designed with the occupants in mind. And with an immersive design option, you have, it's just one more tool in the toolbox. It's not like you're going to stop using like little scale models. It's just one more thing that you can use to think about your design ideas. And in large projects, in fact, the immersive experience is so important for checking details of the design that in large projects, things like we have a builder in our area called Mortensen Construction. They built a new student dorm, 17th Avenue apartments. And Lee was telling me that they actually built out an entire student apartment at a cost of between $100,000 and $200,000 because they wanted to be able to walk through it and make sure that the space was designed appropriately, because any changes that they would have had to make after construction began would be so expensive that $100,000 to $200,000 would be, you know, wasted 3 or 4 times over. But, you know, what if we could use VR? You know, that could save a whole lot of money. And building things out, the problem is that if you decide you want to make changes, it's cumbersome to make those changes in the built-out model so that you can check it again. So typically you only get a few iterations with these built-out models. And they'll build out things for things like operating room. You have to make sure that everything will work in that space. But wouldn't it be lovely to do it in VR? So that brings us to the challenges, and that's, you know, we can do this in VR only insofar as the design decisions that people make in a virtual reality experience are going to be the same as the design decisions that they would make in the real world. And the problem is that for many, many years, and even currently today, people underestimate egocentric distances in virtual reality. So that means if you look at something, it seems closer to you than it really is. And this has been observed since the late 1990s, all the way up to today. It's been a problem that people have looked at in great detail in the years. And I think it would be accurate to say that on average, the underestimation amounts are between about 5 to 25%, even today, even with today's hardware. And just to give you a sense of what this means from a design perspective is if my eyeballs, I'm 5'7", if my eyeballs are 5 feet off the ground, and I need to make a decision about ceiling height, which I actually did. We had our house, we rebuilt our house, and the builder said, do you want the 8-foot ceilings or the 9-foot ceilings? The 9-foot ceilings will be $3,000 more. So that's a decision that only I can make because I know what $3,000 means to me. I know my financial situation. I know what a feeling of spaciousness means to me, and I know what that feeling, if I could make that in the context of my own living room with its size and its windows and everything that affects the feeling of spaciousness, if I could put on the headset and say, okay, these are the 8-foot ceilings, these are the 9-foot ceilings, I could make that decision. But if I've got a 25% distance underestimation, those 9-foot ceilings are going to look like 8 feet. And I'm not going to make the right decision. And even if it's 20%, a 12 by 15 bedroom, which is pretty spacious, is going to feel smaller than a 10 by 12, which is considered small. So people aren't going to be able to make informed design decisions if they've got distance underestimation happening in VR. So like I said, this problem has been around for a really long time. A lot of people have been working on it, and there's a number of different workarounds that have been previously proposed. And I don't want to tell you that what I'm doing is better than any of these. It's just one more tool in the toolbox. So one of the most successful techniques that people have used is adaptation. So people observe that if you put somebody in a headset and then you don't just slap on the headset and ask them to make a snap decision, but you put them in the headset and you allow them to walk around a bit, that they can, over time, recalibrate their judgments or adjust their judgments to be more accurate. One of the issues with adaptation is people are prone to making. You don't want to have to undo somebody's assumption. So you get a client, they put it in, they're like, oh, the kid's bedroom is too small. They walk around, they adapt. They're still thinking in the back of their mind that the kid's bedroom is too small. So you kind of want to be able to do something you could make them adapt, in a different environment and then bring them into so you experience some other space first and then you see your own house. There's ways to get around it. So adaptation is currently, recognized as the best possible solution. Another proposed solution is minification. So the idea here is that if people are underestimating distances, just make everything bigger and farther away so that when people underestimate, they get the right impression. The problem is that when you combine minification, which is a manipulation, a distortion of what you're seeing, with adaptation, which means that people become more accurate over time, you run the risk that your correction is going to then turn into a distortion. So that has to be kept in mind. People have done some research showing that if you put people into a virtual environment and you give them a view that's surreptitiously lower than their own, that will cause things to feel farther away than they really are. Again, it's sort of like the scaling, though, what will happen over time as adaptation takes place. Virtual replica environments is something that my group is involved in a little bit. So the idea here is that if you have a virtual environment that people have experienced before, this is what we found out by accident, actually, in our research. We had our lab, we had people do distance judgments in our lab, we put people into the headset with a virtual replica of our lab, and lo and behold, they weren't really underestimating the distances. And we swapped it around, we put them in the lab, in the virtual lab first, then the real lab, and as long as they'd seen the real space before, they didn't underestimate distances as much. So, it's an interesting sort of from a theoretical perspective, but in actuality, the whole point of using VR for architectural design is that the building hasn't been built yet, and you want to be able to experience it. So again, sort of like the adaptation, you could put people into a virtual replica environment, get them to for whatever reason that works, and then move them from there into another environment and hope that that improves things. And John Kelly has done some research that shows that while that works a little bit, it doesn't work as well as adaptation. So, so there's that. And then the fifth one is self-embodiment. And the idea here is you give people a representation of their own self in the VR. So instead of experiencing the VR as a floating camera, they experience it as somebody who has an embodiment. So the snippets of my research that I'm going to be talking to you guys about today are two. One is diving a little bit deeper into the self-embodiment, and the other is looking at non-photorealistic immersive environments. And so on the topic of self-embodiment, the question that influenced us in our work is, we wanted to, so we were inspired to use self-embodiment by presence research. So when I came to this thing of, why are people underestimating distances in virtual environments, my personal hypothesis was just that people don't know what to make of what they see. In the real world, we live all of our life in the real world. We know the relationship between what we see and the actions we take on the environment. But that mapping between what we see and the affordances for our action in VR are just, a big question mark. And so, adaptation helps erase that question mark a little bit. The perception action correlation becomes a little bit clearer. But, when you just put on VR, maybe you don't quite feel present. You're not willing to immediately, just take everything that you have from the real world and assume that the virtual world works in the same way. But if you give people an embodiment, so the presence research was saying that if there was one thing you could do to make people feel more quote unquote present in VR, it's to give them an embodiment. So that's why we made the big bet and spent a lot of money buying a full body tracking system so that we could do the embodiment. And once we found out that it works, we aren't the only ones that did embodiment. I mean, ideas have a way of kind of buzzing around, and some other research was also done by other people at the same time. But there were different theories about why it works. Does it work because you look down at your feet and you know that your feet are 11 inches, and if your feet are 11 inches, then that must be, 5 feet? Like, do you use your body as a ruler? Or is just the fact of being embodied somehow giving you this gestalt of being, of the VR, having more affordances for interaction that are the same as in the real world? So at any rate, so we poked a little bit more into that, like why does embodiment work and what can we do to make it better? Because embodiment did make things better, but didn't solve the whole problem. And then the second topic is non-photorealistic virtual environments, because with architectural design, it's a lot of time and effort and energy to build one of these models. And one of my students was telling me you'd probably pay $400 an hour to get somebody to add detail to your model. And so you don't want to build out like a totally detailed model and then decide that you want to change something about it. And in particular, it's just not the way the design process works. First you mass out the space, and then after you've massed out the space, people start making surface decisions about surface treatment. And what the architects say is that it's really frustrating when you're trying to get the client to make decisions about the basic kind of structural questions, and then they don't like that it's carpet instead of wood or whatever. They're being distracted by details that are not important at that stage of the design process. And so wouldn't it be lovely if we could put people into sketches and allow them to make decisions about space, and then without having any of the detail present? Okay, so we'll start with avatars. And I'm just kind of lumping a bunch of different studies we did all into one to try to make it a little bit more efficient to communicate. So over several different studies, we compared distance judgment accuracy under 4 different conditions of self-representation. So either people had no avatar embodiment, they had the best possible avatar that we could do at the time. So you see this was 10 years ago. Avatars currently are better than what we could do then, but we did the best we could. And then when we found that the best we could was still not good enough, the question, and I'm kind of telling you the punchline before I show you the data, but anyway, it explains why we did these other two conditions, because we were already doing the best we could, and we had to make a decision of what we were going to do with the next years. Were we going to try to do research to make the avatar representation better? And if so, what should we focus on? And if we did, would that make a difference? Or is an avatar only going to get you so much? And if you want to get better, making a better avatar isn't going to make a difference. So to do that, because we couldn't make the avatar better, we made it worse, and we tried to see, well, if we make the avatar worse, does people's performance get worse? And if so, then we assume that if we make the avatar better in the same way, that people's performance will get better. So we did two types of degradation. One is we took away the motion, and we just had the geometry so people could see their avatar, but it was just a stiff object. It didn't move. We tracked people with the Vicon, and as their root moved, their whole body would sort of slide forward. And then the second was that we had motion only and no geometry. So what people said is, we said, we're going to put you into this bodysuit, and I used to show you the bodysuit, and it's got all these markers attached to it, and when you go into VR, you're only going to be able to see those markers. And so the idea there was sort of like, with sort of the artistic feeling, like if people's imagination space could fill in the body, maybe that would be even better, because that way they can just imagine that the body is theirs. And even if we can't give them a body that's good enough. So anyway, that's what we did. And this is my undergraduate student, Mike Kading, modeling the setup. This is the avatar he picked. Everybody was him. And this is what you saw when you looked down at your feet. So fairly generic. And this is what you saw when you were only represented by markers. And it doesn't look like much, but when you moved, like they moved. And what we did is we asked people to line up their feet with the tape. The reason that we did that is we didn't want to draw people's attention to their avatar representation. We didn't want to say, look down, you'll notice that you have a body, because we thought that might kind of affect things in the study in ways that we didn't want. So we just said, look down at the tape and line up your feet with the tape, then look for the other tape, and then walk to the tape. And we had the tape at some random distance about 8 to 10 inches from where their feet were. So there wasn't like so much interaction that they got to do a lot of adaptation, but they were at least this sort of enforced that everybody did at least, their eyeballs went down to the foot location. Of course, how much that got processed, we don't have any control over. So here's the environment we use. This is a photograph of a hallway in our building. This is a restricted access hallway. You need a special permission to get in there, which I don't even have anymore. So we could be fairly certain that our participants had never been up there. And this is the 3D model of that same hallway that Professor Lee Anderson created using SketchUp and by taking photographs of all of the surfaces. And everything's built out in 3D. The only way you can tell really that it's VR is this. You can see some aliasing in the rendering, and also every single office is 429. But that's it. So here's what we found. When we had no avatar, so what we're seeing here is the percent of relative error, so the distance that they walked minus the distance they should have walked divided by the distance that they should have walked. And this is the error in the real world. So we had people do the task in VR, and we also had people do the task in the real hallway afterwards. We brought them up to the hallway and had them make distance judgments again. And so you can see people are, sort of accurate in the real world, sort of balanced between underestimation and overestimation. There's always a range of individual differences. Some people are, maybe more confident walking blindfolded than others. Some people are, kind of maybe overcompensating a little bit. Some are a little bit more hesitant. But on average, it's about accurate, and that's what others have found before us. But as far as they are in the virtual world, so here's accurate, and you can see everybody is down here. They're between 25 to 40% underestimation, which is for the headset that we were using at the time that we did this work, that was pretty standard. And then, of course, you've always got a few people who are statistically significantly not underestimating, and we find that in every single experiment, and that's what we found. But in general, with no avatar, people were underestimating. When we gave people the avatar, all of a sudden you see all those points move up. You still have a fair number of people underestimating. You still have some people not underestimating. But in general, the people who are underestimating are not underestimating as badly. Now it's going from 10% to 30% instead of what we had before, which was all the way down here. And so when we gave them the stiff avatar, what we found was just a big spread. This person spot on in the real world, underestimating by 50% in the virtual world. And then you've always got your couple of people who are not statistically significantly different, and so mixed. And with the dot avatar, the same sort of mixed results. So overall, this is what we found. With no avatar, people did badly. With the best we could do, people did better. And when we made the avatar worse, people did sort of in between. And so what we concluded from that is that avatars help. And it's probably worth investing the next couple of years in research to give people better avatars. So then the question is what do you mean by better, and how do you give people a better avatar? So there's two possibilities. One is scanning people, their own body, and then animating that, and the other is using video see-through. And so we actually poked into both. And I'm going to tell you a little bit about our video see-through work. So we spent a lot of time taking RGB depth sensors and sticking them on the front of head-mounted displays in order to let people see themselves as a textured 3D model in real time in the context of the virtual environment. This was the PhD research of my student Lauren Fiore, who then went off to Google and is very, very talented young man. The results were lovely, but there were challenges. There's communication latency, so this had a USB 2 connection, and that just wasn't really fast enough. There's sensor noise, because this thing, it uses IR, and the Vicon also uses IR. This thing thinks it's the only source of IR in the universe, and the Vicon is throwing IR all over the room. So, there's a little bit of unhappiness there, which leads to holes and missing data. And then, of course, everything we do with the computer vision, he was a whiz, it all had to be done in real time, so that meant writing a lot of GPU code, and he did the best he could, but it was still just a little bit latency, but the results were gorgeous. So these are screenshots. This is my hand, and this is the virtual environment. You can tell it's the virtual environment because there's just a slight offset on the shadow here, but other than that, it's just strikingly realistic, and it's all built out in 3D, so you can see that even though this is my hand, it's being occluded by objects in the VR that are in front of it. So after Lauren left, I had other students try to make this program faster, and they did make it faster, but they were never able to get the accuracy, the beautiful pictures that Lauren got. So at any rate, this is now some current research trying to compare which self-representation is the way to go. Because whichever, both of these paths are a whole heck of a lot of work. And we need to sort of decide, are people going to do better with a video-based approach? And if so, we're going to fill the hole filling and the blah, 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 blah. And then if the model-based works, then, we need to think about things like, real-time finger tracking and all that. So two separate challenges, and we want to know which way do we go. So we decided to use the visual haptic conflict, Q conflict paradigm. So this goes back to Ernst and Banks, where they found that if you have conflicting information to the vision and the touch, well, people combine those conflicting cues in the order that they trust them the most. And so I thought, brilliant. So we can see if people trust their video avatar more than they trust their model-based avatar. So that's what we're doing here. This is my student Jihang. Here he's using the video see-through to get his two hands touching the block. And here he scanned his hands as a rigid body. and he's being tracked by the Vicon, and the placement of his wrists is determining the location of the hands. And so we trained people in the real world to look at a block and tell us what size it was. Probably took about 20 minutes. We'd show them a block, take it away. We'd show them a block, tell them this is the size, take it away. Show them another block, tell them the size, take it away. Then show them the ones they'd seen before. If they got them right, then we would show them the ones they hadn't seen before. And if they made a mistake, they had to go through the training all over again. So they were spot on in the real world with size. And then we blindfolded them. We did the whole thing again with touch. And then when they were perfect in the real world, we put them into the VR, and so that we knew that we weren't getting garbage from our data collection. And okay, so that's what I'm saying on this slide. And we're still working on writing up this data, and so I don't have it to show to you right now, but the upshot is that we didn't see any really significant differences between the two. We didn't see clear evidence that people were trusting their visual avatar more than their video-based avatar more than their model-based avatar. We also had a condition where people didn't have an avatar, and in that case, they trusted the touch of the block much more than the visual of the block. Even though they could see the block there, they were touching it in the real world, but they didn't see anything touching it in the VR. And so their responses were weighted much more to, oh, I forgot to say, yeah, so we would show them, so they would see a block of one size, they would touch a block of a slightly different size. Sorry, that's on the next picture. So here you can see he's touching this block, but he's seeing this block, or here he's touching this one, but he's seeing that one. And then we'd ask people to report the size of the block, and then they would have to decide how to weight the visual and the haptics. So when they didn't see any hands at all, but they saw the block, they weighted the haptics more. When they had either the video hand or the scan hand, they weighted both. They weighted the visual more, but more the same, but by the same amount more for both hand representations. And each hand representation had its own issues, right? For the model-based one, we didn't have finger animation. People weren't motivated to move their fingers because we just told them to touch the block like this. With the video one, there were, I guess I've got pictures I can show you. So there were, we'd get noise, and we get shadows, and so it wasn't. And we had a tiny little field of view on this sensor, so you're kind of like, you've got these hands sort of disembodied floating around, which wasn't the best. So anyway, we're still pushing on this. We got the new RealSense sensor that has a much wider field of view and supposedly less noise, and we'll see if we can. Yeah, but we don't have the answer, right? I mean, at this point, neither video nor model is superior. So we're continuing to look at video versus model based, because each one has its own affordances. So with the video hand, it's exactly you, but it's exactly you, and you can't do anything else with it. With a model-based hand, it can either be your own hand or it can be somebody else's hand. And so we have a second set of experiments looking at what happens if we give people a hand that is of equal realism, because it's a scan, but it's a scan of somebody else instead of them. And we have them doing a range of different tasks. That some involve tool use, some involve fashion, style decisions, and some involve just a touching task where we look at their speed. And we try to see how the hand representation, how the fidelity of the hand representation, measured not in terms of graphics quality, but in terms of resemblance to oneself, might affect performance for different. We think it's going to affect different tasks differently, and that the jury is still out on that one. I feel bad because I was telling Stephen that I didn't want to tell you about stuff like I'd already done, because you might have heard about it before, but the problem with telling you stuff that I've just done is I don't have all the answers yet. Anyway, and then the third thing that we're doing is we're looking at shadows. So if the problem with a video hand is you've only got the mesh, and so it looks great from like you try to get the camera as close to your eyes as possible. You've got the hand, but the problem is that if you want this hand then to cast a shadow, it doesn't have the volume there to be able to cast a shadow. So Zhihong's got some clever ideas for how to fit an invisible but shadow casting 3D model to the mesh and to let that cast shadows. And then we look at localization, because one of the things that I find the most unfulfilling about video see-through is, I touch this table, and if my hand doesn't my hand, I can see my hand, I can see the virtual table, I've got the real table co-located, I can feel myself touching it, but if I don't have that contact cue, then I still don't really get a sense of how far away I don't know if because we have to check the calibration all the time, and it's really hard to tell if the calibration is accurate or not, because I just get this sense of being disattached from the surface without the contact cue. So we're looking at that. We're also looking at lighting cues, not that we can fix them, but it's just one of the things is with a video, you see what you get, and if we've got a bunch of lights in the room, my hand's going to be lit by whatever illumination is here. But in the VR, if I'm in a dungeon, for example, where it's supposed to be really dark, my hand's still going to be lit brightly, and so we want to poke at what are some of the effects of that. And so anyway, I've just told you Zhihong's entire PhD dissertation, but without showing you any of the data, because we're still half collected and some of it is still ongoing. Anyway, it's exciting work to me. We also did a little bit with Entourage. So the idea here is that it's really kind of a pain to give people a self-avatar, because either you have to scan them, which takes time ahead of time, or you have to get them to suit up and then track them. What if we could just add virtual humans to our architectural models as entourage? So this is something that architects do all the time. They add these little people figures to their drawings, and to bring the drawings to life and to provide a sense of scale. And so we looked at whether we could add intelligent agents as entourage to models to help solve the distance underestimation problem. And we looked at static entourage models, and we looked at animated entourage models. And I've even got some work right now with Stephen Guy, who does intelligent agents work to fill these architectural environments with agents who will know your position and avoid you in a way that is that's more intelligent than just the social forces model. So you can't model people like little balls that bounce off each other, because that's just not realistic. And so he's doing a lot of work in path planning real-time path planning on the part of the agents, so that they behave as real people would. So here's just a couple of pictures. So this is a photograph of my hallway with my student Peng Liu in there. And this is a screenshot of the virtual hallway with the scanned model of Peng sitting in the hallway. So you can see, as far as realism goes, it's pretty high, and we wanted to see if adding the avatars would help. So we actually did this research, and we found out that adding the avatars didn't help, which is really disappointing. And then we even did some follow-up research where we changed the size of the avatar to make them abnormally large or abnormally small, to see, okay, look, if putting a right-sized avatar in there doesn't make people more accurate, are people just ignoring it? Like, if we give them a wrong-sized avatar, will that make them worse? And people just, their distance estimations were unaffected by whatever we did to the avatar, which was kind of disappointing. Anyway, so now I'll talk about non-photorealistic environments. How long do I have? 10 minutes? Till the end of everything. Oh my gosh. Okay, so I'll go a little bit faster. So like I said before, here's our lab space way back in the beginning. This is a virtual model of it, and this is what it looks like when we swap out the photographic textures with textures. So this is just a texture map to the surface. We take that texture and just draw lines over it for the edges. And we wanted to see I said, people were accurate in this model because we brought them into the lab, they saw the lab, they put on the headset, they were still in the lab, and they were great. And so previous research had shown the quote unquote the quality of the computer graphics doesn't matter. And so we thought, well, let's see if we bring them in to this model, and we tell them, we prime them, we say, we're going to put you in an exact 3D replica of the same space that you're in, and we want you to do distance judgments. We see how they do. And what we found was, okay, so here it is again. This is our lab. People were in it. They were pretty much right up along the line. Everybody was not too much distance underestimation by anybody in our group. When we showed them this model and we asked them to do distance judgments, everybody's down here. So whatever it was that was making people accurate, we lost it when we lost the photorealistic textures. And this was really disappointing to us because we thought, okay, so like, what does this mean for architectural design and the possibility of putting people into sketch models, you know, and so anyway, lots of possibilities of why the underestimation was happening. You know, one of them is that like there just wasn't enough detail in that black and white drawing. So what we did is we took the non-photorealistic view and we filled up every white pixel with the color from the photograph. And so now what we have is all of the detail from the photograph, but these artificial lines drawn on top of it that takes away the reality. And what did that do? So just to remind you, here's the photorealistic replica room. Here's what happens when we did it with non-photorealistic, and which one is it going to look like with this third? And this is what we got. So more like the line drawing than like the results in the accurate room. And so what I think is going on is that when you bring people into a room, as long as there's not too much clutter and you put on the head-mount display, people would just spontaneously start saying things like, oh, I can't see you, I can't see my hands, as if somehow what the head-mount display was a magic pair of see-through glasses that made people and furniture invisible. So they were just, you know, they were so confident that the space was the same space. Once we changed the rendering so that the space didn't look as realistic, then, you know, that seemed to break the illusion, and then it was just like any other VR, and they were underestimating. So, you know, we kind of shopped this theory around, and it got sort of poo-pooed a lot. So we decided to look at it from a different angle, and to do that, we decided to look at it from the point of view of starting with a real environment. So here we have a see-through head-mount display where you can look out and see the real world, and we put some cameras in front, which would take the real world, and we had 3 different conditions in 3 different hallways. So 3 hallways, and so the first condition was direct live view of the world through the head mount. Then people saw camera-mediated view of the real world. We had to do this because we knew that people were going to lose accuracy with the camera because the camera's got latency and the camera's got, you know, lower resolution, and the camera is not at the pupil location, and so you're going to lose accuracy that way. And then we have the post-processing of the camera image by a Sobel filter so that it looks like a non-photorealistic style. And what we found was, well, sanity check, people walked longer when we showed them longer distances. People walked the same in all the 3 hallways, just to make sure that there was nothing wrong with any of our conditions. People tended to walk a little bit longer on the 3rd trial than they did on the first 2, suggesting some sort of adaptation might have been happening even though we weren't giving them any feedback. And then this is, you know, where we really get to the punchline. So the lightest is the real view. People did the best with that. And they did worse with the camera view and the non-photorealistic view, but not statistically significantly worse when we took out all of the detail except the edges shown up by the Sobel filter. And so what that suggests to us is, and nobody was fooled, by the way. I mean, we did a bunch of surveys. Everybody knew that they were seeing a camera image that had been image processed. And so the reality of the situation was not in doubt. And so if the experiential realism was equally high in both conditions, it seemed like the visual realism was not quite as important. So we've got plans to extend this to an outdoor environment where we don't have these perspective cues to distance just to see what's going on, because, you know, obviously people are using something to make their distance judgments, and we want to poke around at that a little bit more. So I've got a whole bunch of other things, but I don't think I'm going to have time to tell you about this. A really fun project by 3 undergraduates who were in my lab. This is just using VR to inform design decisions for architects, looking at how the wallpaper pattern affects people's sense of spaciousness in the room, and windows and what you can see through them and so on. But I think I'm out of time, so I'm just going to go directly to the acknowledgements and take any questions you might have.
Thank you. Questions, Dr. Interrante?
That was very interesting. Thank you. I wanted to clarify a couple things. One was that, so my understanding was that when you had people looking at a replica of the lab, that had to be photorealistic in order for it to be fully helpful for distance judgments. And when you replaced it with just lines, edges, and so on, that wasn't helpful, or at least not as helpful. But then in the hallway experiment, it seemed like maybe the lines were as good as the camera images. Am I understanding that right?
Yes.
So
yes.
What's the difference between those two? Why were they as good as the real images in the hallway case, but not in the first case you described?
Because in the first case, it was all in VR. So it was an occlusive head-mounted display. They put on the head-mounted display, and they're just seeing computer graphics. And either it was computer graphics of a line drawing of the room, or it was computer graphics of the actual room, but rendered in a style that left no doubt about the artificialness of its process of generation. And so they knew somewhere in the back of their mind that what they were seeing is computer graphics. Whereas in the other one, they knew in the back of their mind that even though there was mediation going on, what they were seeing was the real world.
I see. So the difference is more about their mindset and what they believe to be true. And that's an interesting point, too, that things like what they believe they're seeing affect their judgments of how far away things are, how large things are, and so on.
Yeah. I mean, and that's straight from Danny Prophet. I mean, he's my inspiration on this. He did that classic experiment where he brought people into his lab, or he did the horizontal vertical illusion. I'm sure you know this. And in the real world, it's like 12%, and on pencil and paper, it's like 8%, or maybe I got it reversed. And then when you put people into the headset, and they think they're looking at 2 people out in a field, it's the real world, and it's 12%. And when they think they're looking at a computer monitor, it's 8%. But the stimulation to the retinal stimulation is exactly the same in both cases, because when they get to the monitor, they just know that it's a monitor because they went like that. But they're seeing exactly what when they think it's a computer monitor, they answer one way, and when they think it's a view of something big, they answer another way. That was just that kind of is so inspired all of my research. That it's not what hits the eyeballs. It's how the brain interprets what the eyeballs are seeing.
Yeah, that's interesting. I have one other question. Going back to your avatar work, that work was done with head-mounted displays that have a more limited field of view. Do you think that the effect of an avatar is even bigger than what you've found there in a modern display, where you actually have a wider field of view and so more opportunity to see your avatar?
That's a really good question, and we haven't done the avatar work with the new head-mounted displays, so I don't know. That's a really good question, because you're right. I mean, with the other one, you kind of had to have some artificial, like, well, look at the tape on the floor to make people notice their feet. Otherwise, you could give them an avatar and they wouldn't even know, because the field of view is so small. So yeah, I think you're right, definitely, that with a wider field of view, there's more opportunity for the avatar to be helpful.
I was going to ask, with the avatars, I've been experimenting with these headsets with eye tracking in them, so that when you look at a very cartoony avatar, if there's a human behind that avatar, then they can do gaze tracking that's very piercing and sort of very attentive. So even if the avatar looks cartoony, I find myself very engaged, because I know there's a human behind it. Mm-hmm. So would that sort of effect override some of the effects of avatars you found earlier, do you think?
Oh yeah, good question. Because the way we set up our experiment, they knew that that the avatar was not inhabited by anybody. We did use a replica avatar though. So my student who ran the experiment, she had a particular outfit. She went and got herself 3D scanned at Mall of America, and then she would greet participants wearing the same exact outfit. So that way, people who maybe didn't know her before, I mean, most people didn't know her before, but they would meet her and interact with her, and then when they put on the headset, there she was. But it was just the virtual her, and they knew it wasn't the real her. And they knew she wasn't puppeteering it because she was like running the experiment. So yeah, I wonder if they thought that that was really her, if that would make a difference. Yeah. That's an interesting question.
Others? Okay, thank you very much for coming.
Thank you.